Okay, so when we look at this one here, okay, this is our graph, 2 over x plus 1 squared. So we have a vertical asymptote at x equals -1. And we want the area between the y-axis and the curve from 0 to 2, from y equals 0 to 0, y equals 2. So we're going to have this kind of unbounded area here. Okay, so the y-axis and that curve there. Okay, so this is an unbounded area, so we're going to have to, it's an improper integral, so we're going to have to at some point use a limit. Now, how do I set this up? Well, I can set this up this way. I can say, well, I want to integrate from 0, and this is not what we're going to do, but I'll show you how it's set up. So this area is equal to the integral from 0 to infinity. Okay, so it's going to infinity, so we should make it into a limit. So limit as a goes to infinity from 0 to a, 2 over x plus 1 squared dx. Okay, so we can use rectangles like that. Okay, so that's one way we can set this up. Okay, using vertical rectangles with a dx width. To integrate this, I guess we suppose that we can integrate that. Okay, so we could do it that way. Now I'm going to set up slightly differently. We're going to use a dy in this case. Okay, so I'm going to get rid of that. And I'm going to use this rectangle here, this dy rectangle going sideways. Okay, so there's going to be a length of x, and our width is going to be dy like that. Okay, so to do this, we need to solve this as an x. Okay, so I'm going to write this as x plus 1 squared equals 2 over y. X is equal to plus minus square root 2 over y minus 1. Okay, so we're going to use a positive side, so we're going to use a positive version of that. So when I set up the integral, area is equal to the integral from, we're going to integrate from 0, y equals 0. Okay, sorry, we need a limit here, so limit as a goes to 0 of a to 2 of the square root of 2 over y minus 1. We're going to multiply it by a width of dy. So there's my integral. So anti-differentiating this, this is going to be y to the power -1/2. So when I anti-differentiate that, okay, I'm going to take this square root 2 out. It's going to be y to the power -1/2, so it's going to be +1/2 divided by 1/2 minus y. That's going from a to 2. Okay, so when we can plug this in, we're going to plug in the values here. So this becomes, I'm just going to simplify this first. So limit as a goes to 0 of 2 root 2 y square root minus y, and that's going to be from a to 2. Plugging in, I'm going to end up with 2 root 2 times root 2, which is 4, minus 2, minus plugging in 0, we're going to get minus 0. Okay, so that we get an area of 2. So that unbounded area ends up being an area of 2. Okay, so this one here, the area between log x and the x-axis, between x equals 0 and x equals 1. So this one here, I want this area in there. Now, fortunately, if I tried setting this up this way, I'm gonna end up with, and this is area, so I don't want displacement, so I want to calculate that as positive. But if I set up this integral from 0 to 1, okay, so limit as a goes to 0 of a to 1. Well, I've got a big problem here because I cannot anti-differentiate log x. Okay, you could always look it up, I suppose, but we don't have a way to anti-differentiate log x. So we need to set this up slightly differently. This is where the dy really comes in handy, because instead of doing, so we can't integrate. But what we could do is kind of phrase this and look at it in terms of an x times dy. Well, to do that, we would make this into an x equals equation like that. Okay, and then we could set this up slightly differently. So we're going to say the area is equal to, okay, so I'm going to have to go to y equals infinity, so I'm going to use a limit. So y equals the limit as a goes to infinity. This is going to be negative infinity, and the integral from negative infinity to 0. And I'm going to integrate that curve, okay, the x value, which is e to the y, so that's my width, and I'm going to times it by the thickness dy. So that e to the y really is the x position, that's how long that line is, and the width is dy. Well, this is really easy to integrate. So this is a much easier problem to solve, because now I can integrate. I just get e to the y. I'm just going to keep my limit in there. Limit as a goes to negative infinity of e to the y from a to 0. Well, I can work that out. That's going to be e to the 1, or e to the 0, which is 1, minus e to the negative infinity, okay, which is 0. So we end up with an area of 1. Okay, so this is one where this ability to shift from dy to dx, so from dx to dy, allows us to use an inverse function, which is an easier integral to deal with.